Welcome to Learning to See the World Through Mathematical Lenses. This course is for students of mathematics, physics, engineering, computer science, and anyone who wants to understand mathematics rather than memorize it. After more than a decade of tutoring and teaching, I've become convinced that much of mathematics is built on just a handful of remarkably powerful ideas. Once you truly understand them, hundreds of formulas compress into a much smaller set of principles. The goal of this course is to help you discover those ideas for yourself. So last week we spent almost all of our time with this quadratic basin. And we kind of started out by just trying to figure out what a volume formula would look like for this basin. And then we kind of got into how the volume would change as you would increase the water level. So to start off, I think it would be nice just for old time's sake to remember kind of the process we went through to get the volume formula as a function of one variable. So we started off by saying, okay, we've got a sneaking suspicion that the basin, the quadratic basin, contains some sort of ratio of its bounding box. And we got that suspicion because in the triangle case, the triangle took up exactly 1/2 of the bounding box in terms of volume. And so when we went to the quadratic, we thought, well, maybe that's also a ratio. So we threw in some constant, I called it C2. And then we went ahead and calculated the volume of the bounding box, which is just length, which is always fixed for us, times width, which definitely varies with height, right? The quadratic relationship between height and width is there, and then multiplied by height. And we said, okay, this is a good guess at what a volume formula, total volume formula might look like, where for any water level, we could plug it in. It'll tell us exactly how much volume. But we didn't want it in terms of two variables, right? We got the lowercase w and h. So we tried to figure out how they were related. And we know they're related by some sort of a quadratic relationship. Does anybody remember how we can find width as a function of height? Any ideas, directions to try? We could start with listing some ordered pairs. So if we've got a height relating to width, that'd be an ordered pair there. And then up here, we would have what in terms of height and width, what would this point be?
Your height and width.
Yeah, absolute height and width, right? And then if we want to interpolate those 2 points with a quadratic, well, we know that we want the width to grow with the quadratic of h, right? So with h squared. And then we could put in width absolute over height absolute squared. And then in that case, when we plugged in the total height for variable height, we would get out the absolute width. And that's what we want. So we found a quadratic that interpolates these 2 points. And this is the one. And then at that point, we could plug it in to our volume as a function of height instead of height and width. So that led to C2 times length times width over height squared times h cubed, because then we had a linear factor there and a quadratic factor for width. Now, last week I kind of presented an argument as to why this should be a constant, but I think I didn't even do it enough justice as is. So kind of the basis of the argument was that nature, well, not nature, we'll say mathematics, has no idea the difference between unit conversion and actual scaling. So in other words, if I write in a multiplier of 2, let's say I have a length of pipe and I multiply it by 2.54. Math could see that as either taking the length of pipe and stacking 2 and then roughly half of 1, right? And scaling it by 2.54. Or it could also be I'm converting from inches to centimeters, right? Math has no way of telling the difference. Those little letters we add on the end, those labels are for us so that we can agree with each other. But as far as arithmetic is concerned, there is no difference. So I really want that to settle in because I think it's a powerful mathematical tool, is that math doesn't really understand scale. As a matter of fact, it has no real way of detecting scale. That's our job. We're the ones who add scale in. So in the case of the quadratic relationship, I kind of pulled this up here and I said, I think I had 2 cases. One was I had a quadratic that went from, say, 0 to 1, and it rose in height to 1. Then I had another case where I had it go from 0 to 100 in the x, and in that time it raised up to 10,000. And the argument at the time was, well, not really an argument, more of a question, is, are these 2 quadratics different? And the answer to that was, well, it depends on the context I give them, right? So, both of these are probably x squared based on what we're looking at. We take the input of 1, square it, we get an output of 1. Down here, we take an input of 100, square it, we get an output of 10,000. But then I went ahead and said, well, I'm going to add units on this. So this one's going to go from 0 meters to 1 meter. And it's going to raise up to 1 meter squared. Because we're plugging in 1 meter into x squared, the unit's going to get squared too. And then I went down here and I said, this is 100 centimeters. And it's going to rise up to 10,000 centimeters squared. And the second I added units in on that, these became identical, right? This would be the same construction. If I handed, specs for this sort of a thing to an engineer and they built both of these, they would actually be identical. So even though without units, they look different, the second we add units, we realize they're the exact same thing. And if you have 2 shapes that are exactly the same, then they have to have the same ratio between the area under the curve and the bounding box. So that was kind of the argument at the time, is okay, if these 2 things that look different before we tack units on, then we tack units on, they're identical. They must, contain that same ratio. At this point, we didn't know what the ratio was. But we do know that, say, if this length is x, so I get a little more abstract, then this length is x squared. What's the area of the bounding box going to be?
X cubed.
X cubed, right? So the area of the box is going to be x cubed for both of these. And so it was no surprise, right, that our volume formula for the quadratic tank ends up with a cube length, right? Because the bounding box of a quadratic has an area in terms of x cubed. So now we just needed to figure out what constant it was. But even this argument, thinking back on it, it's a little bit weak because I mean, I scaled the axes in the same way with the same unit. So in other words, yes, like these two are different ranges of the same quadratic, right? But even without units, these are both kind of x squared, right? They more or less have the same shape. We were just sampling it on different intervals. For this one, we were going from 0 to 1. The other one, we were going 0 to 100. But it was still the same function sampled on different intervals. So that's where I wanted to bring up this other point, which is that we can actually change the unit by which we use on both axes independently. So in other words, I could change the units on the x-axis from meters to inches, and I could change the units on the y-axis from meters to centimeters. They don't actually have to change in the same identical way for this argument to hold. Because say you had centimeters on the y-axis and inches on the x-axis. Well, the area of the bounding box would then be measured in this composite unit of centimeter inch. Right? So that's a weird unit. I've never used it, but you could use it, and the argument still holds. So with this power of independent axes measurements, you can take any quadratic and by using unit conversions, make it look like any other quadratic. And so with that form of the argument, I think it's safe to say that the area under the curve is going to be a fraction or a ratio of the total bounding box. Does anybody have any thoughts on that? Or I know sometimes it kind of feels wrong having different units on different axes. And you can invent units as you like, right? So you can invent any unit you want. This could be 3.14 of that or 6 of that.
I've always kind of liked to think about units as just kind of like a variable that has like an internal multiplier. Like millimeters are just like a times 10 to the -3 to meters, basically.
Yeah. So it's
Up in
really,
this.
oh, go ahead.
Oh, I was saying I think that kind of shows up in this as well.
Yeah. And it's really interesting because polynomials are one of the primary functions that both have an inputted unit and also output the unit, right? We had talked about like logarithms, sinusoids, exponentials, e to the x. You're not allowed to have a unit in the x place when you do e to the x. If you ever use like, I don't know, the Boltzmann distribution or exponential decay, you'll notice that the units in the exponent always have to cancel and give some dimensionless constant up in the exponent. And then they tack on a separate unit once the exponentiation has taken place. So this self-similar argument that we're using for polynomials doesn't stand true for exponentials or logarithms or sinusoids. It's something unique to polynomials, which is really, I think, one of the reasons why we study polynomials so much in calculus is for this reason. So I can safely say there is only one quadratic. If you give me any other quadratic, I can change the domain and the range of my view screen and make it exactly overlay with every other quadratic. That is not true with e to the x. It's not true with log x, not true with sine x. It's very unique to polynomials. And we kind of talked about this in terms of like, if the entire universe shrunk by a factor of 1/2 on one axis only, would you feel like you were pancaked? And I think after some discussion, we came to some consensus that if everything in the universe is foreshortened by 1/2, then there is nothing to compare to in that direction that would give me any indication that I've been pancaked. So, assuming atomic structures can all withstand that, the universe is scaled down by 1/2 in this direction. The ruler I would measure my head with is scaled down by 1/2, and the person I would compare myself with is scaled down by 1/2. there's no way to detect scale in terms of mathematics. Like you can't detect scaling on that level. So with that, we kind of had an idea that, okay, I'm pretty sure this is a constant because it's a polynomial, and math can't detect the difference between unit change and actual scaling. Then after that, once we kind of had an idea that it probably was a constant, a ratio of the bounding box, then we went through a process to figure out what that constant would be. Does anybody remember what the next step on this was? To do with relating changes. So we went and found this change in volume, delta V. And we said, well, if you want to find the change in your amount of volume, what you do is you just take the volume that you ended with. So this would be the final volume, and you subtract off the volume that you started with. And then, of course, all the constant terms that are unchanging, like the parameters of the box and that constant ratio, get to factor out. And this is why Jonathan spent that time playing around with difference of cube. Is because once we got to this point, with the triangular tank, there was a nice delta H that popped out on the other side so that we could relate how height changes to how volume changes. In this case, we need to do a little bit of factoring. And once we factor this out, the difference of cubes gives us H final squared plus H final H initial plus H initial squared. And out pops H final minus H initial. So that's our delta H that we needed to compare the change in volume with the change in water level height. And so we'll just write that as delta H now. All right, and then we use some air bounding. I don't think we're going to go through that whole argument because we spent a lot of time on it. What we did was we chose a triangle wedge like this that we knew would contain the difference between the rectangular component of volume change and the true volume change that includes this triangular wedge and quadratic wedge. And we found out that as you shrink delta H, that this triangular term scales down on order delta H squared, and the quadratic wedge term scales down on order delta H cubed. So as delta H gets smaller and smaller, we are able to actually say that delta V true becomes more and more equal to delta V zero, which is just the constant cross-section rectangular component of the change in volume. And so we took delta H and made it real small. And at that point, we said, well, why deal with H initial and H final? Let's just call it H. Because we're taking 2 points and we're squeezing them so close together that for all intents and purposes, we'll treat it as the same point. And when that happened, all of a sudden, this factoring over here, H final just becomes H squared. H final times H initial just becomes H squared. And H initial squared just becomes H squared. And then we were trying to make it equivalent to the rectangular component of the volume increase. So we figured out what that was geometrically. We said, well, that's just width initial times delta H times length. Length times width initial times delta H. We know width initial can be solved for in terms of height initial. So we did that. And then, of course, the h squareds, they all add up to 3h squared. And things look pretty commensurate on both sides of the equation. What does C, go ahead, Nick. Did you have a question?
Yeah, real quick. Just with this method where we're saying like H initial is basically H final, and we're still saying like with a delta H, we're saying that that's still delta H, but then wouldn't like H squared kind of go to zero, or are we just assuming like a finite change?
Are you talking about this term going to zero?
Yeah, or just we're saying that H final and H initial are basically equivalent by
Yeah.
calling them H squared.
Mhm.
And then so wouldn't delta H either be zero or H squareds go to zero if they're super close to each other?
Yeah, that's a
I guess
good,
H squared would go to zero, but
yeah. So I think, and that was part, I don't know if you've had a chance to watch the last lesson, but what we did was we bounded the error. And so it's not that we're saying that delta H is zero. We're just saying that it's getting very, very small. And
okay.
as delta H gets very, very small, you might have a linear term of delta H and a quadratic term of delta H. And maybe even you have a cubic term of delta H. And the argument is that as you zoom in here more and more, that the linear relation of delta H always has the same look to it, right? It always has that same slope. Whereas the delta H squared, the further and further you zoom in, it practically hugs the y equals zero line. And so does the delta H cubed. So that was kind of the argument is we showed that the errors from the triangular term and the quadratic term go to zero much, much quicker than delta H itself goes to zero. So you can think about what we're doing right now as making delta H sufficiently small enough to where the triangular and quadratic wedges don't contribute almost anything anymore. So it's not that delta H is zero, it's that it's getting so dang close to zero that these two components don't matter anymore. And, that's as practical as you want it to be. You could go as small as you would like. But at the end of the day, delta H itself is not going to zero. And really, this is just an approximation, right? Of course, there's small variations. Technically, H final squared isn't exactly going to be what H final times H initial is, isn't exactly going to be what H initial squared is. But they are close enough to where we can practically equate them.
Okay, thank you.
So this is all really just approximation. And then the error bounding allows you to take as small of a delta H as you need, right? So you can kind of think of, your zoom in window as a little bit of an epsilon delta idea there, right? Squeeze it as small as you want to go. And the ratio is going to get closer and closer to one thing, right? And the one thing that ratio gets closer to tells us that in order for the rectangular part to be equal to the change that we calculated algebraically, that C2 needs to be 1/3 in order to equate the true change in volume to the rectangular one. And so that's when we could come back up here and say the volume formula for the quadratic thing had a 1/3 on it. And so the quadratic takes up about 1/3 of its bounding rectangular present. So that was kind of the argument. We also said, as delta H gets smaller and smaller, delta V gets smaller and smaller, and we stop using delta notation, we start using D notation. And really, the difference I would say here is that with a delta H, you're dealing with two very distinct points, right? And as we're getting delta H smaller and smaller, they overlap almost. So we stop treating it as delta H, start calling it DH, as in at near a point. This is what the change in height is related to change in volume. So that's where we got to. We ended up with dV equals 1/3, or wait, no, LW over H times H squared DH. Another thing you could consider, Nick, and I'm not sure if this would help, is you can actually, so over here we have our delta V. You can divide over the delta H. And actually, you know what, maybe this makes sense first to write out the full decomposition. The other thing we were able to do with this air bounding was we were able to figure out the exact volume that delta V1 holds and that delta V2 holds. And that decomposition ended up looking like this. Delta V equals length width over height squared, H initial squared times delta H. That's the rectangular portion. Plus length times width over H squared, H initial delta H squared, plus 1/3 length width over H squared, delta H cubed. Now, if this helps, Nick, I was kind of shortcutting a little bit here, but if you come up to this spot right here, and you do the substitution of H final equals H initial plus delta H, and you do a bunch of algebra, the algebra will actually decompose it for you. So it's really neat. We were able to do it geometrically, but the algebra also knew how to categorize these things into rectangular bit of increase, triangular bit of increase was delta H squared, and the quadratic bit of increase was delta H cubed. Now, if you start at this point for the limiting argument, you could actually divide over the delta H at this point. And then you're left with length times width over height squared, H initial squared. This term no longer has a delta H with it. But these other two terms retain some delta H's. So this term gets small really quick as delta H gets small. This term gets small pretty quick as delta H gets small. What does this term do as delta H gets small?
That's just a constant.
It's a constant. It does nothing, right? So what we have is really shrinking, stays steady. So as we squeeze that delta H down, more or less, this is all that remains. And you keep this ratio alive on the belief that no matter how small I shrink this, there's still a ratio, right? And that's kind of the idea behind the first derivative, is you end up with dV dH equals length times width over height squared times H. And we stop calling it H initial, we just start calling it H. There's no longer 2 points. We're only interested in where they get close together. Now, before we move on, what can we write this as that might make more sense in terms of width? Is there any way we could use the width formula to rewrite the derivative?
Okay, so just length times the function W of H?
Yeah, it's just length times W is a function of H. What could we call that? On the picture over here.
Like our area.
Yeah. This is your cross-sectional area at some height. So it's really interesting, this first derivative, how volume changes as you wiggle height ever so slightly is actually directly proportional to the cross section, the area cross section. And that makes sense because as we vary it, we showed that if you vary it small enough with h, these two terms are air bounded and they go to zero so much quicker. So the first derivative of volume actually gives us an area. So there's a reduction of dimension there, right? Volume was dimensions length cubed. First derivative of volume was dimension of area. So let's see. That's where we're at. I'd say that's where we left off. Then with this decomposition, there was something interesting I noticed that I felt like was worth discussing, which is, even before we used air bounding to show that this was the true volume of this quadratic bit, we kind of had a guess that that's what it would be. Can anybody think of an example of why the quadratic wedge bit had to have the same type of format as the true volume function of height?
Is it because that's the only one that's still curved on one side?
Sure.
Or
Yeah,
are you
definitely the
are
only.
you like,
Go ahead.
I'm sorry, or I was saying, or is delta V2 like approximating with a triangle?
It's delta B2 approximating which triangle?
The one that you just drew, is it still curved on that side, or are you
Yeah,
approximating as a triangle?
it is still curved. We
Okay.
approximate as a triangle to airbound, but once we actually got the result, we got the true result. And the algebra, like I said, of the substitution spits it out as well. So that's an
Okay.
exact result. It does have something to do with the fact that when you take out a rectangular component and a triangular component, all you're left with is some sort of still a quadratic, right?
Mhm.
With the triangle tank, it was easier to see because all the triangles look the same. Once you cut out the rectangles, you have these triangles stacked up. With the quadratic, it's not as easy to see because they're definitely different shapes. Like they're curved. They're not the same shape, but for a given delta H, they have the same volume. But I was thinking, what would happen if you set your H initial to zero? What would happen to this change relationship between change in height and change in volume?
And the only change of volume would be the quadratic portion.
Exactly. So if you decide to set this as your initial height at the origin, then delta V0, its width is zero initially, right? So you've got your rectangular component of volume is pancake that's got no width, right? And then you remember how we found our triangular bit? Like how did we know where to cut the triangle to leave the remainder of the quadratic bit?
Is it a line that's tangent to the curve at the initial height?
Yeah, we found the tangent line to the curve at that point using similar techniques as we have been, and that's how we cut it. So, if you start at h initial equals zero, what would be the tangent line to the quadratic base? Yeah, Nick's got straight up and down. So the triangular bit pancakes too. And of course, we could just plug in and see, right? Oh, delta V0 has an H initial term. So if H initial is zero, delta V0 is zero. And same with delta V1. And then all that's left over is the quadratic wedge, like Jonathan said. So if that's the case, then you could say H initial is zero H final is H. V initial is 0, because if you start at the bottom, it's got no volume in it. And V final would just be a function volume of H. If you plug that into the change relationship, you end up with V of H equals 1/3 length times width over height squared, and then H minus 0 cubed. Well, H minus 0 is just H. So you just end up with H cubed. So in other words, this bit had to match the volume formula. Otherwise, for the case when H initial was 0, it wouldn't have perfectly matched. That quadratic remainder wouldn't have perfectly matched the true volume formula. So this is an interesting thing about polynomials. If you can find that last slice, you automatically get the volume formula out of it. So if you can whittle away the rectangle, whittle away the triangle, whittle away the quadratic, then that cubic chunk that's left over for the next tank, if we were to go that far, we're not going to, then you would be able to, if you found the cubic little wedge, that would automatically give you the cubic volume function. So next up, I'd like to talk a little bit about something I call construction versus equivalence. I think we've talked about it once already, where we had the different sized vessels, right? And yet they all had the same volume to time curve, so long as the faucet was the same for all three, right? Yet underneath of our actual graph of volume to time, we noticed, hey, they're not exactly the same. At some point, these tanks are going to overflow. And then the max volume in the tank will matter. So I think in math, oftentimes what we're doing is we're finding an equivalence between two systems. Here's a system we want to understand. Here's a system we do understand. We find a way to make them equivalent. In making them equivalent, though, we often lose information, right? We simplify the system so we can understand it, but there's always information loss. And so we need to be really skeptical whenever we do these sorts of things, that we know what we're losing in making an equivalence. All right, so starting with the geometric separation, right? We've got the change in volume is the change in volume caused by rectangle, plus change in volume caused by triangle, plus change in volume caused by quadratic bit. And from there, we've got the relationship we pulled apart earlier. Oh, got to square that h then. Squared. Initial delta h squared, and then plus the quadratic bit. So when we talked about the derivative, remember we said that dv was really equal to cross-sectional area times dh. That was with really small delta h and delta v. We were able to get it down to just the cross-sectional area. But that was for an instant in time, right? At a point, not between 2 points. So my thought is, what if we take our true difference, delta v, that's the true change in volume, and we go ahead and factor out a delta h from each term. And then we're going to ask what each of these terms represents short of a delta h. So we pull a delta h from each term, so we get a delta h out here, so that we can somewhat align this differential form with the finite difference form. So we already agree that this represents the initial cross-sectional area, right? And that's what remains when we take the derivative, right? Because these delta h's get smaller, they go to 0. This guy doesn't have a delta h, so he doesn't go to 0. But when we're in finite difference, these things also represent a weird kind of area. Okay, so over here I have the tank filling from H initial to H final. It's got a rectangular portion, it's got a triangular portion, and it's got a quadratic portion. I've decided to make somewhat of an equivalent tank out of a rectangle because I understand rectangles intuitively. That's where I do my best thinking. Rectangles and triangles. So what I did was, well, with the delta V0 chunk, I just replicated it identically. So those blue portions are exactly the same shape. We've got over here, we've got delta V0, same volume, and same shape. But then for the triangular bit, I'm not so keen on triangles. So I equivocated the area, or I'm sorry, the volume. I made the volume equivalent, but I morphed it from a triangle into a rectangle because I understand rectangles better. Then with the quadratic bit, did the exact same thing. I made the volumes equivalent, but I figured out what width it had to be and what area it had to be to contain the same volume as the quadratic slice, right? And my argument over here is that with the true finite difference over here, when I factor out a delta H, well, all three of these rectangles have an area. Here's the area of the rectangular equivalent volume. Here's the area of the triangular equivalent volume, area of the quadratic equivalent volume. Each of those get multiplied by delta H to extrude this thing out and find total volume. So my argument is when I factor a delta H out of my true difference relationship between delta V and delta H, that what I get in here is basically the equivalent rectangular cross section. To match the triangular wedge. Specifically in volume. So I'm matching volumes. And then this term over here is going to be the equivalent rectangular cross section necessary to match the quadratic wedge. In volume. So I've got two systems here. I've got the true system, it's quadratic tank we're filling. And then I have what I'm calling an equivalent system over here, where I've shifted everything into rectangle land. And it's cool that the math naturally factors out in such a way to tell me exactly what this cross-sectional area must be and exactly what this cross-sectional area must be to match the volumes. What are you thinking, Nick?
So I apologize, I got a text real quick, but for this delta V, are you saying that's the delta V of the true volume thing or the delta V of the extruded rectangular one?
Oh, I'm sorry. It's both.
It's both? Okay.
Yes, because I've matched the volumes equivalently.
Mm-hmm.
Now,
Okay.
Where this argument came from was this was the true volume formula, change in volume formula that we came up with. Rectangular, triangular, quadratic. And all I was saying is, well, hey, the derivative kind of informed us that a small change in volume is just cross-sectional area times a small change in height. So I thought, wouldn't that be interesting to take it away from just differentials and work it out in finite differences, right? Instead of approximation, like calculus is doing. So
I have a question.
Well,
Sorry, I didn't mean to interrupt you.
I was just going to say, saw the delta H out here, so I decided to pull a delta H from each of these. And then the things that remain must be the cross-sectional areas of the equivalent rectangular slices that I would use. Go ahead.
Sorry, so this is kind of like, so you're factoring out the delta H, and this is kind of like what this wedge over here would have looked like as a rectangle at the start, kind of like. So that's what this is saying, basically.
I would just make one addition. It's not what it would look like at the start, it's what it would look like across the full interval from start to finish. But then that naturally leads to the next question, which, I mentioned when we come up with equivalent models, they're rarely equivalent. That's why I say construction versus equivalent. The same construction can lead to multiple equivalences, but there's things you lose along the way. So what did I lose in going from the quadratic tank to this equivalent volume rectangular prism?
Um, it doesn't change by height, so it's only good for this particular interval.
Yep. So what you're saying is I've tailored it to just this interval, right? So it's not going to work for other intervals by nature. Um, does it agree at the start and the finish? So in other words, would both of these tanks, if I started filling them with the same change in volume, would they both end the interval at the same height? Assuming the fill rate's the same, right? They have the same function.
Yes, if that height represents the same volume for both.
Yeah. So the whole point was I made them equivalent volume over the interval. So if I start filling them at the same rate, then they will both reach the same height at the end of the interval at the same time. So that's the way in which they're equivalent. Now I want you to think mid-interval. Are they going to agree on water level height mid-interval?
No, the rectangular one's going to be at a lower height.
You think it's going to be at a lower height the whole time? And what's kind of the argument behind that?
It's not the whole time, but I guess initially, I'm not sure where that change would happen, but initially it's going to be at a lower height as you start. And then at some point, well, I guess that it would have to catch up only at the end. I don't know.
Yeah,
Yeah.
no,
There,
yeah, I think you make a good point there. It's that with the true quadratic basin, the initial cross-sectional area is smaller than my equivalent rectangular prism cross-section. So initially, we would expect the quadratic basin to kind of shoot ahead in water level, right? And then the rectangular basin is, of course, going to go at a steady rate, assuming you're filling it steadily. But at some point, it's got to catch up. Like you're saying, Jonathan, it's got to catch up because we know they're going to end the interval at the same time.
the rectangular fill rate is just going to be the average of the quadratic fill rate over that interval. I think.
Yeah, that's spot on. So, if we're just doing, say, from this point to this point, and let's say we're graphing height volume, what's going to happen with the quadratic basin is initially it has a smaller cross section. So it's going to fill up much quicker at the start. And then its rate of change is going to slow down. Because at some point it's got to be wider than my equivalent rectangular prism. Whereas, and once again, we're assuming constant flow rate in these models. You could always plug in a non-constant flow rate, but that's going to make the graphing harder. Whereas with the equivalent tank, under a steady fill rate, it's just going to be a straight line, right? We're going back to our first lesson there with constant flow rates and constant cross-section tubs. But it is cool that we're able to make a rectangular model that at least agrees on the start and the finish. Right? So this is an equivalent model that agrees on the start and finish. And yeah, Nick's exactly right. The slope of this line right here would be the average change in height. So it'd be like almost delta H over delta B. Whereas the true fill is going to start out with a slope higher than that. And then at some point it'll have a slope equal to that, according to the mean value here. And then it will have a slope less than that, but they'll meet up at the end. All right. So with that construction versus equivalent, I suppose the question would be, what would we have to do to, well, actually, maybe, you know what, there's probably a few more good questions in here. What would the width of this be compared to the width of this, or the width of this compared to the width of that? Does anybody have any ideas on how those different changes will relate? So over here, I have change in width 1. That's the linear change of the width over that interval. Then I have delta W2. That's the quadratic change in width over the interval. Together, they combine to give the total change in width. And then over here, I have my constant cross-section equivalent tank labeled with W1 and W2. So I'm curious, how do you guys think that the total change in width 1 is going to relate to width 1?
Would it be exactly half?
Yeah,
It's a right triangle.
exactly. So if we're trying to make a rectangle have the same volume as a triangle, then it needs to have a factor of 1/2. So delta W1 is going to grow to double what W1 is. Because this is going to have to be twice as wide at the end to make a triangle have the same volume as its equivalent rectangular prism. Then what about for delta W2?
Is it going to be 3 times?
I think that's a good guess. I'm curious though, because with the triangle, it was like nice and straight up and down. But with the quadratic bit, it's kind of at an angle. So that might be an interesting one to dive into. We do know the
Don't we
width
have,
formula. What's that?
sorry, I was saying, don't we have the formula for that volume or that area,
Oh yeah,
like
you're
that
right.
cross section?
Over there, huh?
And
Yeah,
then we can just like,
it does. It is 1/3, isn't it? There's a 1/3
oh
out
yeah,
there, but this one doesn't have a 1/2. So keep that in the back of your head. We'll see why that is in a minute. But I just wanted to show how we can decompose the widths real quick here too, to show that that's the case. So that's our width formula. We can find delta W total pretty quickly by the difference of squares. So you get the HF plus H initial, delta H. And then let's see here, we've got delta W1. We talked about finding that through tangent lines, right? So we had to know the tangent to the quadratic at that point, and then basically took a linearization, a linear step forward of delta H in height to see how much delta W1 was. In order to do that, we had to use a similar limiting process that led to us finding that dWdh was 2 width over height squared times H. So yeah, that would be our slope. So to find delta W1, you do a linearization. You take a finite step forward delta H with that instantaneous slope. And when you plug that in, you get delta W1 equals 2W H over H squared times delta H. I suppose I should be writing H initial there. And so that's our delta W1. And then to find our delta W2, we can just subtract out of our total change in width, we can just subtract width 1, right? Because change in width 1 plus change in width 2 is the total change in width. And in order to do that, let's see, delta W is width over height squared, H final plus H initial, delta H. And then we're subtracting off delta W1, the change in width caused by the linear term. Everything lines up pretty nicely there to where, let's see, we would end up with width over height squared HF delta H plus width over height squared H initial delta H. And then minus 2 W over H squared H initial delta H. And so that would end up giving us what? Width over height squared HF delta H minus width over height squared H initial delta H. And then we can factor out the constants. And that gives us width over height squared delta H times H final minus H initial. And what's H final minus H initial?
Delta H.
Delta H.
Delta H. You need another delta H term there. Delta H squared. All right, so we kind of look at it and it seems right. Because if we pull a length out of this to get the change in width, right? I suppose maybe it'd be good to write that out. You could say delta V equals this jazz, rectangular cross section, plus, and then we've got length times, really, this is delta W1. Or wait, is it W? It's W1. Length times W1 plus length times W2, right? Length times W1 gives us this cross-sectional area. Length times W2 gives us this cross-section. And so when we look at that, and then we look at what we solved delta W2 for, delta W2 is this. Delta W2 is that. W2 is that with a factor of 1/3. So Ramsey was right. Delta W2 is 3 of W2, my equivalent widths. And you can also look here, look at what delta W1 had in it. Had a 2 in it. Right? So W1, that's why there wasn't a 1/2 up here. Like we kind of expected, is because delta W1 itself had a 2 in it. And so that 1/2 just canceled out with it. But yeah, at this point, I just kind of want to just want to point out kind of what I'm getting at here is we can pick whatever interval we want and find an equivalent and average it out. It's not going to agree at the midpoints, but it's going to agree over an interval from the start to finish, right? So this is kind of hinting at what comes next, which is what would you do if you wanted a more accurate version of this model, this rectangular model? If it doesn't agree at the midpoint, but it agrees at the endpoints, what might you do to extend this model to make it more accurate?
Yeah.
Make more endpoints.
What's that?
Yeah. I think Jonathan said shrink delta H, and I said make more endpoints.
Okay, both, right? Simultaneously, right? The more you shrink delta H, the closer that curved line is going to be with the linearization. And if we just stack a bunch of these tiny, nicely rectangular prism cross sections on top of each other, then you can get very accurate. Now, at this point, you might just say, well, I'm just going to use the volume function, right? You could just use the volume function. But another thing to point out is that a function is only as accurate as you are willing to sample it, right? Oftentimes we think about functions as smooth curves. They're really just a bunch of question marks until you plug in inputs and get an output, right? You put it on your graphing calculator, it slices it up too and plugs things in and gets the output. So this idea of shrinking these equivalent prisms and stacking them, it's not that much different than just plugging in a bunch more values to evaluate your function on a finer interval. Any thoughts on this before we move on to the next page? Interesting, we're seeing these patterns show up repeatedly of the one, the 1/2, the 1/3, right? Keep showing up. And they're going to keep showing up, especially as we get into higher order differences, right? We had fun with the triangular tank on this one. Quadratic one is a little bit more hairy, but I think it's doable. So, we had talked in the past about, okay, we've been dealing with this change in volume operation a lot. How much does the volume change as I go from some height initial to some height final? But what if you're interested in how your change is changing, right? Then you would apply a difference of the difference. You could think of this as a change in how the volume is changing, or change of change. And we often write it with a delta 2 being just to save room. So we're just applying that difference twice. And does anybody remember how we did that? How do you apply this change operation twice?
Yeah, you need like 4 points. Or
Not
was
quite as many, but close.
3 points, so then you share the middle one, or
So
I missed last time. So.
no worries, we're taking a change in the changes. So, whereas before a single change might have been, say, how does our volume change as we go from point 1 to point 2? And that would be represented by this kind of area there. And then we might say, oh, well, how does our volume change as we move from 2 to 3? That would be this one here. And to find our change in the change, we're actually going to take our final change, that's our delta V from 2 to 3, and subtract it from our initial change. That's our delta V from 1 to 2. Now you could write this out, and I think it's neat. You would have like V3 minus V2, and then minus the second change is V2 minus V1. And if you distribute the negative sign, you end up with V3 minus 2V2 plus V1. And so this is how often, like a lot of computer programs will approximate a second derivative. They'll do it with a second finite difference. And you'll start noticing, and I think, Jonathan, you starting off with your drawing and the fact that your coefficients were 1, 3, 3, 1 was pretty cool, right? Because, okay, the coefficients of the second difference is 1, 2, 1. The coefficient of the first difference is 1. Binomial theorem it shows up a lot in calculus. It shows up in these finite differences too. But I would recommend against evaluating the volume function at height 1, height 2, height 3, because we actually already have, for some initial value, we know what delta V is going to be equal to. And I'm going to write it out by factoring out this term so I don't have to write it over and over again. Also, the Wakeham's starting to glitch out, which is never fun. H initial delta H squared plus 1/3 delta H cubed. All right, so we already know like a standard form for our change in volume between two endpoints. So what would happen if I just plugged in for this? What would happen? Somebody let me know what to write down for that. Second change between points 1, 2, and 3. So what would I plug into my standard first change to get the change from 2 to 3?
Do the delta H's just have 2 and 3 on them?
Oh, yeah. I kind of want to avoid this, even though it's neat to look at. I don't think it's the most practical way to run this, but these delta H's all are the same. So that's one thing I forgot to mention is that we want to compare apples to apples. So we keep the delta H with which we're comparing changes identical. But I guess what I'm asking is, if this is delta V from 2 to 3, what's the initial value?
E2.
Yeah.
Or,
So
yeah.
instead of H initial, I'll plug in H sub 2. So what's cool is we got this change formula in terms of just initial height and delta height. And so that's what we get for the change from 2 to 3. Then we subtract off the change from 1 to 2. And of course, the initial height there is just H1. All right. Anybody notice anything neat that's going to happen? Any simplifications?
I'm guessing you're going to get another term with H2s in them that's going to cancel out.
There is actually there's shapes that don't depend on initial height. And those shapes are the quadratic wedges. Notice the quadratic wedge terms. Remember, we noticed this earlier. They don't have H initial. They only depend on change in height. And so for that reason, the fact that we're starting at two different heights doesn't matter. And actually, the quadratic terms get eliminated after the first difference. So the first difference, there was a quadratic term. The second difference, those quadratic terms are identical, and they annihilate when we take the difference of differences.
And that second term on that last equation, does that need to be an H squared on the LW over H?
Probably, yes, thank you.
Okay.
I always forget that H squared. It's really important. It's got to be there to keep things dimensionally correct. So, all right, we get that to cancel out. I'm going to go ahead and once again factor out this length width over H squared. And notice what else we have. This minus sign distributes to all those, right? So what we can write now is actually H2 squared minus H1 squared, for H initial, times delta H. So those were our delta H terms paired up. H2 squared, h1 squared minus sign between them. Then we can do the same thing with the delta h squared terms. You got an h2 minus h1. We get h2 minus h1 times delta h squared. Now, this is what's so cool. It's like there's a recursive nature to these polynomials. We keep seeing tricks that we used on the triangular basin showing up as we reduce order. So how do we factor this guy out?
A difference of two squares. So h2 plus h1 times h2 minus h1.
Yeah. And then that's just another delta h term, right? So we get a delta h squared. And then h2 minus h1, that's just another delta h term. So we get a delta h cubed. All right. So now we've got the second difference. This is its true exact form. And now I kind of want to point out geometrically what's going on. So if we were to say move the change from height 1 to height 2, if we were to move it upwards, it would look something, let's see here. It would look something like this. But of course, it would be curved. So this is the difference of differences right there. We simply take the first difference, we superimpose it on the second difference, and whatever remains that hasn't been covered is the second difference. Now, what's really interesting, though, is that notice over here, we have some terms that are order h squared, and we have some terms that are order h cubed. So the order h squared terms, as we start shrinking this interval, those terms, I'm sorry, the h cubed, delta h cubed terms, as we shrink the interval, are going to disappear quicker than the delta h squared terms. So kind of looking at this region right here is kind of your order delta h cubed. These triangles that remain are kind of your delta h squared. And what we're going to do is we're going to slough our delta h cubed term when we squeeze h closer and closer. So we're squeezing h1, h2, and h3 closer and closer together. And actually, maybe just to make the argument feel even a little more natural, let's just divide everything by delta h squared. And what we're left with is, I keep forgetting that squared there. Let's see. H squared. And then what we're left with over here is h2 plus h1 plus delta h. I'm going to distribute that length width over height squared. Yeah, so that's what's left. So as we shrink delta h, as we get delta h closer and closer to 0, of course, without ever reaching it, this second difference is related as a ratio to the square of the change in height. This term shrinks with delta h. This term stays constant roughly the whole time. I mean, I guess it doesn't stay constant during shrinking because as h2 approaches h1, like they're technically different values, but it's certainly staying more, it's not shrinking, we'll say. h2 plus h1 really turns into just 2 times h as h2 approaches h1. And so what you end up with then is this second derivative. And it's much harder to interpret what a second derivative is as compared to a first derivative. But I think there's a neat way to tie it into those equivalent tanks we were dealing with. So now we've got a 2 out here. And yeah, 2 length times width over absolute height times height. That's what we end up with for our second difference. Or our second derivative, I should say. If you pull the length out of this, you're just left with width over height squared. Or 2 width over height squared times h. I'm pretty certain that that was our delta W1. Or related to our delta W1. I'll have to look back. But what we have there, let's see here. And also notice the dimensions of it. What's the dimensions of the second derivative here? Got a length and a length and a length over a length squared. So the dimensions of our second derivative is actually a kind of length. Whereas our first derivative's dimensions, what was that again?
Was area?
It was area. So we're seeing kind of that reduction of order, right? We went from, okay, the volume changes with height, like the cross-sectional area. Now we're asking how the change changes, and out pops a length. And that length actually relates to how these widths are changing. So in other words, the first derivative says, hey, you have some cross-sectional area. If you times that cross-sectional area by delta H, you'll get some volume. That's what the first derivative is saying. The second derivative is saying, we're going to actually extend our width a little bit. We're going to extend our width and see how much area gets added on. So it's a surplus of area that's being added on. So when you add on more volume, it's through area times delta H. When you add on more area, it's through length times delta H. So the dimensions work out. And if we get back to this original form that we had of the delta V, wish I would have left it written up there in its original form. Maybe I should have just written it in LaTeX so I could copy and paste it over. So our true change in volume had this term. That was the rectangular bit for the increase. Then it had this term, which was the triangular decomposition there. And then it had the final quadratic bit. Over h squared. Delta u. Wait, yeah, cubed and squared. Okay, so this second derivative, does it relate to any of the rectangle, the triangle, or the quadratic? And if so, how?
Is that just the last term there?
This one? Does this term have an h involved? This one has a single h there. So which of our terms has a single h, where height initial grows linearly, or makes it grow linearly? The rectangle, the triangle, or the quadratic?
Triangle.
It's the triangle, right? That has the h term. All we need to do to turn this into this is multiply by a delta h squared and divide by 2. So in other words, what I'm really saying there is this first term is really just dv over dh times delta h. That's the cross-sectional area initially times the change in height. That gives you the volume of the rectangular bit for the first difference. Then we add it to half of d2vdh squared. I'm sorry, my pen is not doing well. Oh my goodness. Times delta h squared. So that's all we had to do to get from the second derivative to the triangular wedge volume, is we had to divide by 2. We kind of saw why in the last slide, right, with the construction versus equivalence, is that the width of the equivalent rectangle to get the same volume as the triangle was half, right? And then we'll go one layer deeper here. So where we were at is we were saying that the first difference is really, we found out it's just dvdh times 1 and then times delta h. And then the triangular bit could be found using the second difference, or the second derivative, by taking 1/2 of d2v dh squared times delta h squared. And then, of course, we got the additional term that we have to account for. So let's write it out. Well, the writing's working better, so that should save time. So we still haven't accounted for that quadratic bit in terms of higher order differences or derivatives. But that should naturally come next. So we ended off with, I think was delta 2v. Oh man, I wish I had it written down somewhere. Let's see. I think it was delta v1, 2, 3 was length times width over height squared times h2 plus h1 times delta h squared. Or no, times just delta h plus, or wait, no, it was squared. Plus just delta h cubed. And we decided when we took that second difference and we turned it into the second derivative that we could approximately neglect that delta h cubed term. Now we're going to go another order higher, so we have to go 4 points now to get the third change. And the third change is just the difference of 2 second changes. So the second change from 2 to 3 to 4 minus the second change from 1 to 2 to 3. And by the way, if you spend the time to write these out in terms of first changes, you'll find, I think that it ends up being v4 minus 3v3 plus 3v2 minus v1. So there's those coefficients we saw Jonathan reach with the cube. What was it, completing the cube earlier? But since we already know what the second difference is, we may as well use it. All right, so what would the second difference for 2 to 3 to 4 be? We know it for 1 to 2 to 3. So what would we shift in here to make it 2 to 3 to 4?
Just change H2 and H1 to H3 and H2.
And honestly, up here, we probably could have done this. I feel bad I didn't. We could have written H2 as H1 plus delta H. But it's not the end of the world. We'll get to the same place. So we've got H3 plus H2 delta H squared plus delta H cubed. And then subtract the difference from 1 to 2 to 3, which we already have. Anything cancel?
Delta H cubed is gone.
Yeah, those higher order terms don't depend on initial heights of their intervals. So those are going to go away. We get another reduction of order. And then at this point, what we get, probably going to try to write it all in terms of, well, I guess, well, let's just see where it goes. So if we were to subtract that, wouldn't we get H3 plus H2 minus H2 minus H1 with the delta H squared? And then those H2s cancel. And I think it's important to point out that for some of these, right, for some of these approximations, finite difference to derivatives, we've had to use limiting arguments, right? Oh, delta HQ is going to go to 0 much faster than delta H, right? In this case, things are canceling real nicely for us. And we're just left with, I think, H3, couldn't that be written as H1 plus 2 delta H? So H1 plus 2 delta H gives us H3. And H1 plus 2 delta H, then we're subtracting by H1. So then those cancel. And then we have, let's see, what would that give us? 2LW over H squared times delta H cubed. So this last derivative that we're kind of finding, we divide over the delta H cubed and there are no higher order terms anymore. They're all gone. And we just have the 2LW over H squared. So, this one's actually constant. This finite difference doesn't change. It's completely related to constants and the size of the tank. So there's no H in there, there's no delta H in there. So for our third derivative, with respect to H, we just get a constant, and it's just 2LW over H squared. And that has similar format to this, to the quadratic bit. So what would we have to do with D3V DH cubed? Whoops. To turn it into looking like this term or the increase caused by the quadratic bit? We've got to change a 2 into a 1/3.
So divide by 6.
Divide by 6. Then, I mean, it's got the L, the W, and the H squared for free. And then what?
delta H cubed.
Yeah, we got to have the delta H cubed. So what you're noticing here is what's called sometimes a power series. But essentially what's happening is we've found that these higher order derivatives can actually relate back to the changes driven by linear and quadratic terms. So in other words, this is the change caused by the linear increased constant cross section. This is the change in volume driven by the triangle, right? And this is the change driven by the quadratic bit. Now, does anybody have an idea as to why this constant didn't end up being a 1/3? Because we seem to have this thing of well, with a rectangle, it's a full version of its bounding box, so that's a constant of 1. With a triangle, it's a half, so it's a 1/2. And with a quadratic, it's a third of its bounding box, so it's 1/3. So why do you think we're getting 1/6 here? All right. So let's say I'm trying to find the area under a rectangle, and then I'm going to graph that value. So I want to graph how much area is under this rectangle. What is that graph going to look like? What's that, Ramsey? Oh, sorry, I thought you were answering.
No, sorry, I was talking to myself.
So if we graph the area under a flat line, it actually ends up giving us a triangle. Because each step we take along the rectangle, we're adding the same amount of area. So linear constant increase. And that triangle, it brings with it a factor of 1/2. Then when we find the area under a triangle, we've kind of noticed that that ends up giving us a quadratic. And the area under a quadratic, that adds a factor of 1/3. So there's kind of a recursive process here with these power series, because we were taking these differences multiple times over, that we tacked on a factor of 1/2 for what was 1/3 and ended up with 1/6. So you've got 1 over, what is it? 1 factorial, 1 over 2 factorial, and 1 over 3 factorial, because you've applied the derivative 3 times to get there. So you have to apply the accumulation 3 times to get back. First time is an area of 1, second time is an area of 1/2, the triangle, third time is area of 1/3. So that's where that factorial comes in. It's just really the product of the harmonic series up to that point. 1/6. And that's all good and fine. We've got about 20 minutes left. And what I'd like to do is point out that this whole time we've been focused on absolute finite differences. And that ties into accumulation, because this is what we would call accumulated volume. That's how much the volume has changed. It's not an exact amount, is it? Right? There might have been an initial volume. And then we added some more volume. That's the accumulated volume. And if you want to know the total volume, then you take the volume initial and you add the accumulated volume, and you get a final volume. Or with height, right? The delta H is accumulated height. Same type of argument. But man, this thing is not easy to compute. That's a lot of terms. It's kind of gross, but it's perfect. So in other words, if you give me a delta V, I will find you the delta H. If you give me a delta H, I will find you the delta V, and I know it's exact. The geometry is exact in this case. But one of the tendencies that we've seen in this course so far is that if you shrink delta H small enough, these higher order terms matter less and less the more and more you shrink delta H. So it's natural to want to get from something this complicated and convoluted to maybe something more like just this. And as Nick mentioned earlier with the construction versus equivalence graph, I'll go back there. One way you could get this kind of an equivalence more accurate is by stacking equivalences on top of each other, right? I'll take this section of the quadratic basin and turn it into a rectangle. I'll take this section of the quadratic basin and turn it into a rectangle. And like Jonathan said, squeezing those delta H's smaller and smaller so that those higher order terms matter less and less. And so ultimately, we get to a place where we don't want to evaluate this much. Or, polynomials are kind of special, right? Without that scale symmetry argument, we wouldn't have come up with the constant of 1/3, right? It really hinged on scale symmetry in order for that to work. And the fact that math doesn't know the difference between true scaling and change of units. So we got something special here. Not all functions are this special. So what we're going to do next is take this, we're going to take this true change in volume for the true accumulated volume. And we're going to break it down into little chunks of equivalent sizes to the accumulated volume. And once again, kind of make an error scaling argument to come up with something that looks a little nicer and a little neater. And so the argument there is going to hinge on this. I'm going to say, let's make delta V and delta H very small. I'm going to use curly delta here so that we don't get confused. So if I wanted to write this as maybe something like this, square curly delta H. Think of curly delta as like a little bit bigger than D and a little bit smaller than big delta. And we get H initial delta H squared plus 1/3 delta H cubed. All right, so, and now I'm going to draw a volume graph, volume to height graph. And I'm going to say, let's say I know some initial amount of volume in the tub. So I have V initial. I may actually, just for the sake of clarity, just call it V naught. So V0, that's the initial amount of volume in the tub. And then I'm going to say, well, I know that I can take an absolute volume difference for some change in H. So I'm going to change the height by some amount, curly delta H. And I know that my volume is going to increase by some amount, curly delta V. And I think I'll call it curly delta V 0, 1. It's going to be between the 0 and 1 interval. So I have the exact formula here to figure out that change in volume if the water levels change that much. So I can come over here and put that there. And as we know, it's not going to be a straight line that interpolates those 2 points. As Jonathan pointed out, it's going to be more of a curve. But if I get my delta H sufficiently small, the curve starts to look like a line a little bit. And I at least know that my start point and my finish point are accurate. perfectly accurate. Then I might wish to take another step delta H. I'm going to keep my delta H as the same size. And I know that I'm going to have an increase of volume curly delta V from 1 to 2, from interval 1 to 2. And once again, that's not going to be a straight line. It's going to be a curved line. But the start and the finish point are absolutely correct. So I'm really just sampling my function more and more. And then you would continue this process up until whenever you want it to end your full change in height. And ... you have some V final. And that's the volume that you're at. It's the initial volume you have plus the accumulated volume you gained along the way. I might call that V sub n. And I suppose I could call this like H0, H1, H2, all the way up to Hn. And really my argument is this, it's that if you take delta V and you sum it up, starting at 0, H0 up to n, that you will get the total change in volume from intervals 0 to n. So in other words, if I take my volume at the end and I subtract my volume at the beginning, I can break it up into a sum of these small changes in volume that, by the way, are perfect. This is perfect. It's absolute. This is the truth. But it's still complicated to compute. So what we'll do next is I'll fill in what dV is. Well, actually, maybe even before that, I'll say, is delta V any different than delta V over delta H times delta H? Are my finite differences in such a way that that works? Maybe a better question would be, what does this represent? What does delta V over delta H represent on this graph?
That's just your slope, basically.
Oh, right. It's your slope sampled at some point K.
Mhm.
So right here, my volume to height function has a slope. And that slope would be delta V over delta H at the 0 point, when H is 0. I can then take a step delta H, and that linearization will bring me to the next point. Okay, so this is really rise over run information at any point you want it, right? That's what the sub K is. It's like, hey, just plug in whatever point you're interested in the slope at. This will give you that. And then the delta H is a run. So really, dV over dH sampled at some point times that step forward just gives you a linear interpolation between 2 points of known change in volume, is what that gives us. And then we do it again, right? Here, the next step, we would sample this point and we would find how is our volume changing as we change height here at height 1? And then plug it into our formula, our change relationship, and then do a linear step forward. And once again, we know the endpoints are accurate. At this point, this isn't an approximation. The only thing we're approximating is that we don't know the information between the points. We're just drawing a straight line. But we do know that it will give us an equivalent increase in volume so long as we use this true relationship, this true decomposition of triangles, quadratic wedges, and rectangles. But then I think, as Nick mentioned, you may decide, oh, geez, I shouldn't use that, should I? No, you know what? I think I will. So I'm just going to say the limit as n approaches infinity. So I'm going to break the fourth wall here. And what we've got here is all we're saying is take smaller steps, right? That leads to more evaluations of this, but it gives us more accurate data in between the intervals. The other thing it gives us, which is nice, is that as n approaches infinity, what does delta H approach? If we slice this up into tons and tons and tons of little subintervals, what happens to our delta H, or our step in the H direction?
Is it getting closer to the big H?
Not quite. Are you talking about this big H, the big change in H?
Yeah.
Well, if we're cutting it up smaller and smaller, as a matter of fact, when I write this, I'm saying we're cutting it up infinitely many times. How big is the width of those intervals?
Getting really small.
Getting really, really small.
Yeah.
So as we increase the number of sample points for our slope, really delta H is approaching 0. So I'm going to use that. It's in line with what we've been doing. Now I'm going to plug in into our sum here. I'm going to plug in our true delta V over delta H. So delta V over delta H is equal to length times width over height squared times H initial squared plus H initial delta H plus 1/3 delta H. And I'm claiming that really, actually, I didn't even need the limit for this to give me an accurate output, because remember, this is exact. So if I start here, I could even take one step and end up there. And it would be an accurate initial and final point. Would not be accurate in the middle, but it would be accurate at the initial and the final point. So if I cut it up, it's still going to be accurate. But where the limiting argument comes in is as delta H approaches 0. Oh, whoops, it looks like I forgot to tack on this delta H running. There. What's going to happen, as we shrink delta H to this relationship? I mean, what's happened in the past when we shrink it?
Are those terms going to go away when you shrink?
They're going to shrink much quicker, right?
Yeah.
So I would still come to the point where I would say, based on what we've done here, I would say you could take delta V from 0 to n, so the full change in volume, and say that it is approximately equal to just the limit as dh approaches 0 and sum up all the slopes times their runs to get the rise. And what the heck, let's knock off those terms. Just an approximation, right? And what we end up with is LW over h squared times h initial squared times dh. And this was actually our derivative, wasn't it? That was our first derivative. So that's dv dh times dh. And then in a similar way as when we shrunk the interval down for differences, we went from delta notation to d notation. When you start summing up more and more things, you go from summation notation into a tall curly S that stands for sum. Does this look familiar to anyone? The thing that got Leibniz and Newton famous. People were doing calculus way before them, but this is really the tie-in that Leibniz published first, and Newton later proved he had stumbled across before Leibniz published. This is the thing that tied up the areas to the slopes. Okay? What do we have in here? We have a slope. What do we have out here? We have finding the area of something, right? This is called Fundamental Theorem of Calculus. And it shows how intimately related area under the curve is to the slope of the curve itself. So you notice you've got a slope. If you find the area under the slope curve, you get the change in the function itself. But at the end of the day, I think this theorem is less about integrals and derivatives undoing each other and more just about, like, how simple is that idea? Just add up the little changes and get the big change. Like, we all understand that intuitively, yet the fundamental theorem of calculus often feels scary. But that's really all it's saying, is add up all the little changes and you get the big change. Now, what I have written here is an approximate sign. But as we talked about, we know through air bounding that as we shrink delta H, these terms matter less and less. And that process can go on as long as you want it to. You can make delta H as small of a finite thing as you'd like to. And as an engineer, you probably will, right? But the point is that with this kind of a limiting argument, you get to the point of just saying, well, it's pretty much equal. And that's what we've been getting to. But yes, the area under the curve changes based on the slope. Because if you have a higher slope, there's going to be more area under the curve. You got a lower slope, you're getting less area under the curve. That's how they're related. And then I suppose the last little thing would be, this is still really useful. This, or I guess I deleted it, but you remember we had delta V true equal, what was it, dV dH times delta H plus 1/2 second derivative with respect to H times delta H squared plus 1/6 d2 VDH or d3 VDH squared delta H cubed. Oh, and we forgot to show why the fourth derivative was 0. It's because by the time we got to the third difference, they didn't depend on initial height. So those ended up canceling, and beyond that, it's always 0. So This is still super useful technique, right? It's called the Taylor series, and it's often what you use if you can't integrate a function to find the total change in it or the total accumulation. But at the same time, you may have some derivative information. Derivatives are often easier to find than integrals. Easier to find the slopes of things than it is to find the area under the curve. So this actually gives you a method within you can take a large step of delta H and get an accurate delta V, right? So you can take a large step of delta H and you still get an accurate delta V. Whereas we talked about before, if you just simplified it like this with like a pure linearization, does this work very well for large delta H? Right, as with the triangle example, the larger your delta H, the larger that triangular wedge term gets, the larger the quadratic wedge term gets, you can no longer neglect them. So you've got two methods of finding the same thing. You just want to find the total accumulation of volume. And you can do it through using linearizations many, many, many times. Or you can do it through finding first, second, third derivative information and multiplying it in this fashion. So with that, I think next week what we're going to start talking about is motion and how this relates to motion. A lot of the same principles arise even when we're not just talking about volumes and tanks. So I think that's where we're going to head. And then hopefully we'll be able to come up with a water clock at the end of next lesson. Has anybody given any thought to how they would make a water clock that that builds or drops at a uniform rate? There's one way that's kind of a cheat. It's kind of cheating, in my opinion. You guys remember those two assumptions we started the course with uniform flow?
I believe so. Yeah.
What's that?
So I believe so, the uniform flow, so it won't be changing over time.
Yeah, do you remember what assumptions we made about the faucet?
That it's like a continuous, like the average stays the same pretty much
True.
no matter how.
We said constant pressure, right?
Yeah,
How could you keep a tank like a water clock under constant pressure?
you could be filling it with more water.
Right. That's kind of the cheat code is you could just have a reservoir, right? You just always keep this thing full and you always have water flowing in to keep it full. And then you just have a spillover, right?
Mm.
So because there's a spillover that goes elsewhere, then you know that the orifice at the bottom of the clock that's feeding, the gradations you're reading, that's always under constant pressure because you're keeping the fill reservoir at a constant height. So that's a cheat code. But there is actually a way to make a certain shaped water clock that drains at a certain gradation per unit time uniformly. So if anyone was interested in a challenge, I would say we have the skills from what we've done here today in order to figure out what shape that would be. So if you're interested over the next week to try to explore that before we get to it in class, I think that would be interesting. And there may be more than one shape that does it, right? If anything we've shown today is that there are many different constructions that lead to equivalent outcomes.